group rings.
Okay. Okay. Thank you for having me, Holger. Thank you for inviting me. So I'm going to talk about K-theory of group rings. So we have a ring. And a group. And then we form the group ring, consisting of all finite formal linear sums with coefficients in R over the group. So it's a finite sum. And the coefficients are elements in the ring. And we multiply using the multiplication in the group, right? So this. Okay, easy examples. If we do this to the infinite cyclic group, then we get the Laurent polynomial ring. If we do this to a finite cyclic group of order P, this is really strange. Sorry. Okay, then we get a quotient of the polynomial ring. What else is to say? So one reason we might be interested in the group ring is that an RG module is the same thing as an R module with a G action by R linear maps. Another reason we might care about this comes from topology. So if we have a reasonably nice space, then we can form its fundamental group acting on the universal cover, and then all of algebraic topology on the universal cover becomes not linear over Z, but linear over the group ring, right? So, for example, if we look at the homology groups of the universal cover, and this is an RG a module over the group ring. Okay, so in algebraic topology, we have to work with these group rings. And finally, the group ring is clearly more complicated than the ring itself, because we have the inclusion of the ring as mapping to the unit element in the group here, and then we can use the augmentation to go back. Right, so R factors through the group ring, which means that, I mean, if we want to say anything about the group ring, we should have understood the questions about the ring before, or we should phrase the answer in terms of something about the ring. Okay, and that's the general sort of goal or slogan of this is, can we understand the group ring, and in particular its K-theory, in terms of the ring? Of the ring and maybe the group, right? Can we split questions about the group ring into questions about the ring and questions about the group? Okay, and so I'm going to get rid of my starting time. No, ending time, sorry. So first I want to discuss this from the point of view of idempotents or K0. Okay, so just to fix the notation, the idempotents of a ring are the elements that square to themselves, and obviously 0 and 1 are idempotents in every ring. And every idempotent in R is, by this inclusion map, also an idempotent in the group ring. So the group ring has at most more idempotents than the ring. It cannot have less. If we take for R ring without zero divisors, then of course, since idempotents are zero divisors, we are only left with 0 and 1. And if we then take a very mild group, like say the infinite cyclic group, then we can, if we look at an idempotent in here, we can look at the lowest or highest coefficient, right, and then see that all idempotents, I mean, the only idempotents in here are actually 0 and 1, right? So adding z here to the ring doesn't add any idempotents to the ring. Okay. On the other hand, that's not the general picture. So an easy way to get more interesting examples is if we have H a finite subgroup in G, and if we pick our ring such that the order of this finite subgroup is invertible in the ring, then we can form this sum, and this is an idempotent. Okay, so in this case, this game of splitting up the question into questions about the ring or the group, it doesn't quite work. We really have an idempotent that kind of uses the ring and the group at the same time. Right? It's not of these simple forms. Okay, on the other, yeah.
So you said if R has zero divisors, then
without this supposed. Yeah, no. It's never good to have zero. Well, maybe it is. Okay. Okay, and conjecturally, one needs to have either this or this condition to fail to get any idempotent. So this is a conjecture of Kaplansky. So he said if R has no zero divisor, so let's say R is an integral domain. And G, right, in order to avoid this example, it should be torsion free. Then conjecturally, all idempotents in the group ring are trivial. It's only 0 and 1. Okay, so this was from the point of view of idempotence, but we've seen that K0 is defined in terms of idempotence. So we have this map that, given an idempotent, produces an element of K0. We simply take the idempotent and the ideal generated by it is then a finally generated projective module over the ring and gives us an element in K0. So instead of studying idempotence, we might be interested in studying K0. And then there is a similar conjecture. So that's called K0 conjecture. The same assumptions. So R is an integral domain, and G is torsion free. then the conjecture says, again, nothing happens. K0 of the group ring is no more complicated than K0 of the ring, which we can phrase as saying that K0, well, tilde, by which I mean here the quotient by what we get from the K0 of R is 0. Okay, and the remark, this K0 conjecture implies Kaplansky's conjecture for, in certain situations, for example, if R is a field of characteristic 0. Okay. Good. Okay, so that was a discussion about idempotents, or K0, and now I want to have the same discussion about units, or K1. So the units.
This needs a smooth, R has to be smooth, regular to this.
Right. It's wrong to say, right, sorry, thank you. It's not quite the same assumption. We need stronger assumptions, so we need R to be regular, yes. Right, we need more. Same assumption on the group, but the ring, we need better assumptions on this one. Regular, okay, so regular means it should be Noetherian, and every finitely generated module should have a finite resolution by finitely generated projective modules. Okay, but right, maybe you just want to remember Z and fields are regular. Okay, so maybe these are, even then these questions are very complicated and maybe are the most important cases. Okay. Okay, so units, and as before, every unit in the ring gives us a unit in the group ring, but now there is a second source of sort of canonical units that Andreas already pointed out. Right, every element in the group is a unit in the group ring. Basically, that's what we did. When we formed the group ring, we added the group as units to the ring. Right? And those are combined, give us this, products of units in R and elements in the group, and those are called canonical units. Okay. And then, as before, if actually we had a mild assumption on a ring if it doesn't have any zero divisors, and look at a very easy group ring, namely the infinite cyclic group, then we can play the same game and find that all units are canonical. But again, this is no. If I regular is when I'm going to make the K1 statement. This is just units. Right? You just write. Okay. You look at the highest and lowest coefficient and play a game. Yeah. Okay. Good. But on the other hand, if we have torsion, then interesting things happen. For example, if we have an element of order 5, then this element turns out to be a unit. Okay, and even for the infinite cyclic group, so for R nil, idempotent in the ring, say r to the n is 0, then we can form 1 plus rt plus r squared t squared plus rn minus 1, tn minus 1, and that's a unit in the group ring over the integers. Right? For the easy answers, such as these are all units, we're going to need assumptions. And yeah, maybe I can put this right here. Okay, so Kaplansky conjecture, I mean, not only this, but also about units that under these assumptions, all units are canonical. Okay, let's see. Okay, so just as before, idempotents give us elements in K0, units give us elements in K1, which we can define as the abelianization of the general linear group, and then units are just invertible 1-by-1 matrices, so we get elements. But we already discussed that that's not going to be enough, right, to account for all units, because we've seen the group here, and similar, the group will show up in K-theory. So let's do this as follows. First, we have the easy map, so K1 of the coefficient ring maps to K1 of the group ring, but also first the group maps to K1 of the group ring, and then since the target is abelian, it factors over the abelianization. But then we can make this a little more complicated. We can tensor with K0 of R. So if I have, say, a projection in here, and a group element in here, and we're going to send it to P times G, and on the complement of the projection as to the identity. Okay, so this gives us unit. This gives us invertible matrices over the group ring, and therefore elements in K1. Okay, and this accounts for sort of things coming from the ring and things coming from the group, and then the K3 version of the conjecture is that this should be everything. So K1 of the, let me do it like this. The White group relative to R of our group, which we define as K1 of the group ring, dividing out the images of these two maps. So we divide out K1 of R and K0 of R tensor the group ring. Sorry.
So can you explain why this is an invertible matrix? Is PQ plus 1 minus 1?
I mean, the inverse on this summand is G inverse, and the inverse of this summand is the identity 1 minus P and P times 1 minus P0, so they don't mix. I mean, it's just like, I mean, it's G and this is here I have P and here 1 minus P.
Oh, it's in K0 of R. Okay, yeah, so.
This was supposed to be a projection. Okay, good. Okay, and just, I mean, it already came up in Andreas' talk, but one reason why one cares about this, and in particular, one cares about this in the case where R is the ring of integers, is the S cobordism theorem. So this time, M should be a closed manifold. Its dimension needs to be at least 5. Then S cobordisms over M are in 1-to-1 correspondence with the White group over the integers of our group G. And the map is exactly the one Andreas explained. I mean, an S cobordism is a manifold. Sorry. H cobordisms. An H cobordism over M is just a manifold which has two boundaries. One of them is M, the other is very good point. Thank you. Right, the group that we have around, the group that algebraic topology forces on us by what I said at the beginning. Okay, so an H cobordism is a bordism between M and some other manifold such that the inclusions here are both homotopy equivalences. And then we can form the Whitehead torsion as explained in the previous talk, and this exactly classifies H cobordisms. In particular, it's going to be trivial if and only if the associated torsion is 0, and if the H cobordism is trivial, this means it's just a product. It means the other end is homeomorphic to the thing we started with. And that's a key step in many proofs that show the two manifolds are homeomorphic. Often what one has to do first, one first produces a bordism, then one makes it into an H cobordism, and then one tries to check that its torsion vanishes and that the two ends are in fact the same. Okay, so that's a good, yeah? Pardon? From here to here? Yeah, this is exactly the Whitehead torsion that Andreas explained. Right, it's the inclusion of this, right? This is the homotopy equivalence. We want to know whether or not it's simple. That's exactly right. And on the other end, you have to construct something, right? I mean, this gives you a matrix, and you need this matrix then to build a manifold using going on handles. Okay. Then I want to state the Bass-Heller-Swan theorem, which tells us that we know exactly, well, depends. We know a lot. Well, okay, we know this. We know the following about the group ring over the infinite cyclic group. Namely, it first has a summand, just the K0 of R. We know that has to be here by this inclusion and augmentation. And then there is a copy of Kr minus 1 in the case of star being 1. This comes from this map that I discussed here, okay, but that exists in general. But then that's not everything. There is a further group that appears in 2 copies and is related to nilpotent endomorphisms. So this comes from nilpotent endomorphisms and is exactly related to this sort of construction of a unit, right? I mean, those things can be non-trivial in K-theory, and then they give us elements in here that don't come from the ring or the shifted copy of the ring. Okay, but this is 0 if R is regular. And that's why one has to put regular in the K-theoretic, in the assumptions of the K-theoretic conjecture. Okay. And maybe, well, yeah. Did I get it right? I think it's, I wanted to put star minus 1 because, I mean, so, okay, okay, so.
You're correct if you use the notation in my book.
Well, then it must be right. Well, let's give a definition. So, nil star of R is the K-theory of some category, of an exact category of nilpotent endomorphisms on finitely generated projective. And then I need to kill something too much that's there.
You should have killed it there.
Why should I have killed it here?
When you
Oh,
killed
then?
it there, you line up with the K-theory of R.
Okay, so.
And you don't need to tell that on top.
Okay? No? Okay, well, anyway, modulo sum tilde, that's the right notation. The official notation. Okay. Okay, so we discussed idempotents, units, and how they come up in group rings. We had Kaplanski's conjecture, and they have, I mean, they're K-series versions of it, so to speak. But now, of course, there should be a conjecture if for all of K-series, not just for K0 and K1, also for higher K-series. And to this end, one needs the Lodé assembly map. So this is a map that has as a target the group in question, the K-theory of the group ring, and its source is as follows. Okay, so here by this symbol, I mean, homology with coefficients in the K-theory spectrum. So maybe let's first say, okay, no, this is the generalized homology theory associated to the K-theory spectrum of R, right? We discussed in Chuck's talk that higher K-theory can be defined as homotopy groups of a space, but then in fact those are homotopy groups of a spectrum, and whenever you have a spectrum you get a generalized homology theory. Is that vaguely familiar to most? Okay, so good. Pardon?
It doesn't matter if it's
Well, it's going to matter sooner or later.
star is negative,
Right.
but
It's going to matter sooner or later, and then I want it non-connective, but
it doesn't matter unless you take star negative.
well, no, that's not right. I mean, if I have homology in large degrees here, it's going to pair with negative K-theory here, so it's going to make this group bigger if I have negative K-theory here, even if star is positive. So this is actually it's important to. I mean, the conjecture I'm going to formulate is that we're going to make R regular again, and then we don't have to worry. But for the general conjecture, it will be important to have non-connective K-theory. We'll come to it. Okay. This is the homologous, and then BG is BG. So, right, BG is the CW complex characterized by pi 1 of BG is G and no other homotopy groups. Oh, and let's see. Right, I should have said something important first. Maybe I can sneak it in here. Right, so in particular, right, if we use the homology theory associated K-theorem spectrum, then we know what happens on a point. If we evaluate on a point, we get the K-theory of the coefficient ring. And then we can use a spectral sequence to try to compute the value on some other space, for example, BG, assuming we know what the K-theory of the ring is. Okay. Ta-da. Pardon? I was trying to say that if I put in a point in this theory, then what I get are the K-theory groups of the ring.
That's not a statement of, okay.
So here this was supposed not to connect, and the sentence here was supposed to go on, right? If we use the K-theory spectrum, then in particular we know what happens on a point. We get the K-theory of the. Okay, good. Okay, and maybe just let me point out that this is the homology of BZ with coefficients in the K-theory spectrum, right? The classifying space for Z is the circle, and we know how to compute any generalized homology of a sphere. We just get the coefficients, so we get K star of R, and then we get a copy shifted by the dimension of the sphere, which is the other copy here. Okay, and so the general version of this conjecture says that under suitable assumptions, this should always happen. So No further, yeah. Sorry. So now this conjecture gets a name. Even though what Chang stated in written is slightly weaker, but or slightly more careful maybe. This is the Lode assembly map, and the claim is alpha is an isomorphism. Okay, so the claim is we can compute the K theory of the group ring by computing this homology group. Right? And you should think of this as being easier, because it's split up the group ring again in an ingredient that comes from the ring, the coefficients, and homology of the group on the other side. Okay? And because we have tools to try to compute generalized homology, we have a chance of getting our hands onto this. I'll say something about this later, and then maybe you ask another question, and then we can play ping pong a little bit. Okay. Okay, right. And it implies the other two statements I had before here, because, so let me put a remark here. Where is it? So this is, again, under the assumption that R is regular, and we have no negative K theory, then H0, we just get the contribution from the ring. So we just get K0 of R. And if we use H1, then we get the contribution from the ring, but then in the spectral sequence we get another contribution, which is the other summand we had here. So it's K0 of R tensor with the visualization of the group, which now maybe we want to write as the first homology group of G, or first homology group of G. Okay, so this remark is supposed to explain that the conjecture as formulated here, if we go back to star equals 0 or 1, is exactly what we had before here. Okay. So the assumptions that the ring is regular and the group is torsion-free are both necessary. We can, from the discussion of interesting elements in K0 or interesting elements, interesting idempotents or interesting units, those also lead to counterexamples to alpha being an isomorphism. As soon as you give up R as regular, then you can use, and then immediately you get this from here, from the Bass-Heller-Swan's theorem. And if we have torsion in the group, then we can, for example, detect these idempotents we had before and give us more elements in the K theory than is supposed to be there by this homology group. Yes?
Is there a refinement with more general setting?
Yes, thank you for asking this, because then I'm going to, this is what's come next. So we want a general conjecture. Okay, I'm very happy. Okay, so, but before we can discuss this, we need to revisit the discussion of this assembly map that I didn't, of this Lode assembly map that I did not define. Okay, so now we're going to need the language of Davis and Luke. Okay, so they construct a G homology theory. I.e. a functor I'm going to write like this, but maybe let me emphasize that what goes into the construction of this gadget is more complicated than just the K-theory spectrum of the ring. So therefore I put Davis-Luck here. So they construct a G homology theory, so that's a functor defined on G spaces to created abelian groups and has all the usual properties, excision, long exact sequences, Majority torus, homotopy invariance, and so on, such that right before the theory I just erased is without the G was determined by what happens on a point, and there we use the K-theory spectrum. Here, for G homology theory, at least if we want to evaluate it on GCW complexes, we need to know what happens on orbits. So we need at the very least to know what happens if I put in an orbit, G mod H, and the answer is supposed to be, or the answer is, the K-theory, but now of the group ring of the isotropy group of this orbit, right, of the H that we divided out. Okay. And then for X free GCW complex, so right, you can there's an equivariant structure of a CW complex, and the action is free. We get that the equivariant theory is just this theory we had before by quotienting out the group action from X. Okay? Right, I mean, if we have a free GCW, we can imagine we could try to compute this by decomposing it into cells and then going down to cells, but then there's only one type of cell, namely G mod the trivial group, so we only need the K-theory of the ring itself, right, the group ring over the trivial group. Okay. Right, so in particular, the left-hand side we had before can be expressed in this equivariant language as the equivariant homology where we pass from BG to its universal cover EG. Okay, and then I can tell you what the assembly map is. Right. Now we can just take the map that sends EG to a point, also known as G mod G, and if we put this into our theory, then we go to, I should have left some space. Okay. Which by design was the K-theory of the grouping. Okay? So now I've defined the map, but I didn't define this homology theory for you. Okay. But now it is, let me see. Okay, so now we have the opportunity to add isotropy here, right? To make the left-hand side more complicated, to account for the stuff that this conjecture does not pick up. Okay, and this works as follows. So I need to talk about classifying spaces for families, and here families refers to collections of subgroups of our group G. So F is a family of subgroups of G. This just means it's a set of it's a collection of subgroups that's closed under two operations, namely conjugations and taking subgroups. And whenever we have such a family, then we can build another space, another G CW complex, GFEFG. So this is again a G CW complex, and it can be characterized by its isotropy spaces, subspaces. So if we take, right, we have the G action on our G CW complex. If we take the fixed subcomplex, then we either get something contractible or nothing, and we get something contractible exactly when H is in F, and otherwise nothing. Right? So in particular, if we used the family consisting just of the trivial subgroup, then we only want to get a fixed point if we take here the trivial subgroup. So if we have the whole space, so the whole space is contractible, that's correct for the universal cover of BG, and otherwise we don't want anything. Okay, and this space sort of is designed to sort of study the group relative to the subgroups in this family, right? Because those will now, I mean, those are not unwrapped in this space because they have fixed points, but G as a large doesn't have a fixed point in this space, so it's somehow unwrapped over the space. Okay, and this space is, so this is unique up to G homotopy equivalence, just like a BG and EG weren't really spaces but only homotopy types. And then we can define an assembly map relative to a family of subgroups. Right, we just we just put in this space that allows for some isotropy in this equivalent theory, take the map to the point, which is then the K theory of the grouping. Okay, so this way we can make the left-hand side as complicated as we wish by adding more and more subgroups and getting a better chance to end up getting everything on the left. In particular, if we were to allow G itself to have a fixed point in here, then we would just make the left-hand side by definition the same as the right. So for this to be useful, we should be geizig. We should be cheap about which groups we allow here. The fewer groups we allow here, the less complicated the spaces, the more useful it would be to have this comparison map. Okay, and this is then what Farrell-Jones conjectured. They said sort of the first thing, right, from our discussion before, we know we cannot take the trivial subgroup. We have to take into account finite subgroups, right, because we had already these elements in, right, these idempotents. We have to take into account the infinite cyclic group because of this nil phenomenon. And then the first thing that sort of combines them in a nice way is the family of virtually cyclic subgroups. Right? So a subgroup is called virtually cyclic if there is a cyclic subgroup of finite index. Okay, so this is a very natural way to throw into one family finite subgroups and the infinite cyclic subgroup. Okay, and their conjecture is that the corresponding assembly map is an isomorphism. And this is now for all rings and all groups G. Okay? Maybe one should add that at the time when they made their conjecture, they were kind of careful and said this should only be taken as an estimate that fits all known data at that time, more than 20 years ago, but it still fits all data. So everything we know about K-theory of group rings is consistent with this conjecture. And that's where I want to stop for today.
Thank you. Other questions?
So if you knew the conjecture for all regular rings, would that apply for all rings?
No. If I knew the conjecture for not that I know. No, I don't think so. I have no theorem to this effect. I know of no theorem to that effect. But what I should have said, and I thought that's what you were asking, is that this conjecture implies this again. Right? So this Farrell-Jones conjecture is more general than this one. Okay? Basically because this is only about torsion-free groups, so the only added difficulty here is that we may have infinite cyclic groups on the left. But we know what the K-theory of infinite cyclic groups is by the Bass-Heller-Swan formula. And then if we assumed regular, then no nil terms appear. And so we can deal with this, and then it comes out to be this conjecture.
Can you give some indication of something that we know this is true for?
Yeah, we know. Okay, so the very first thing Farrell-Jones, Farrell-Jones, before they made this conjecture, they were very careful to prove a lot of cases, right? So to have some evidence. So I wrote that people were worried about virtually abelian groups. Right? That maybe the family one had to use were all virtually abelian groups. But no, and then they checked before they made this conjecture. But generally, so the method they pioneered is whenever you have non-positive curvature around or negative curvature around for your group in one way or another, then you have a good chance of proving this conjecture. So in particular, they proved this for fundamental groups of non-positively curved manifolds. And this has been taken much further now to hyperbolic groups, K0 groups, all lattices in Lie groups, and more groups. So now we really know that's true for a lot of groups, but there's still many more groups. So the general slogan is, I don't know if that's, one general slogan is nothing that's true for all groups. Everything that's true for all groups is a trivial statement, and since this doesn't look trivial, chances are there might be a counterexample, but who knows.
So how computable is the left-hand side?
Well, you're in the land of generalized homology, so you have a spectral sequence which you can try to compute this, and it works best if you can get rid of your family. So in particular, if your group ends up being torsion-free. And maybe the ring is regular, because then you're in this bigness again. Pardon?
Finding out this EF is not a problem?
Say this again?
Is finding out the EF?
Well, we can write down something that's the EF, then it's a huge thing, just like writing an EG is. Right? We can write down one. That doesn't mean that we can compute its homology.
Is there a conjecture about the units of a group ring if the group is torsion-free and the ring is just any ring, not necessarily the domain?
No,
That's only this Idempotent part, like maybe modulo the Idempotent things, it's only the triple units or something.
Oh, you mean, say again, well, the answer is going to be no, but nevertheless, what do you want?
Well, you have these two contributions, one coming from the Idempotent parts,
Right.
cyclic subgroups, and then you have the triple units, and maybe they generate everything.
Right. So for torsion-free groups, maybe. Yeah, I don't know. This would be sort of the analog of this conjecture, right? This says everything in here is nil or it comes from the homology group. And in what we called the unit conjecture, I didn't call it that, but I mean, in Kaplansky's conjecture about units, the thing that wasn't accounted for is nilpotent phenomena, and maybe there's a conjecture that says that's only, but I don't know.
Somehow the step from the unit itself to K1 is much more drastic because you also linearize. That's of course the drastic process for non-dimensional groups.
Right, but that's a good point because I had this little remark that from the K0 statement one can get back to Kaplansky's statement about idempotents, but there is no such thing for units and K1. So there it goes. Yeah.
Has anybody looked at, like, the assembly map of finite coefficients, maybe finite coefficients away from the finite subgroups that arise?
Not that I know of.
Maybe this is probably a problem session, we should ask it.
So back to my original.
So you give us this other more complicated gadget.
Right.
And then the definition is simple, but the gadget is really mysterious. So is just repeat it again. Is there a way?
So right. So I'm.
In the chatting place, or just the Lode assembly map. Is there any way to describe that?
So you're asking basically to describe this.
No,
This-
that's the Lode. I'm asking you to forget that. Even though I'm sure it's beautiful.
Okay.
Just the map. You should get a map from BG smash.
Yeah. Well, sure there is, and maybe Holger knows, but I don't.
It comes from multiplying group elements and matrices, right? So
Yeah,
G
okay,